All right, now based off of the graphs, how can we find the key features of a function? So we know in the first column, that if we're given the graph of f, we see like the increasing and decreasing because that's where the graph is going up or down. The relative min and max is where the hills and the valleys are, so on and so forth. When we get down to concave up or concave down, we can tell that the graph is cupped up or cupped down, so hold soup or doesn't hold soup. Okay. And then, so what we are really going to explore is what happens when we have the graph of f of x and f double prime of x. If we have the graph of f of x, we will, or f prime of x, excuse me, f prime of x, we will use these cues. So we know the graph of f increases when f prime is positive and f prime is negative, the graph decreases. We can tell that we have a relative min or max when there's a change between positive to negative of f prime. F prime also tells me where to find my critical numbers when our y value is equal to 0 and so in other words, the 0 of the function. So if I graph f prime, the zeros right here would be the critical numbers. On the graph of f prime, if the arm is increasing, we know the graph is concave up. And if the arm is decreasing, the graph is concave down. And then we can also tell where the points of inflections are by looking at the relative max or min of the graph of f prime. All right, so let's move on. Let's do some examples and we'll come back to that. All right, so we have to be really careful about what's given. We are given the graph of f of x, so I will go ahead and write that in, and we need to find all of the things. So we're going to find our critical numbers. Remember, critical numbers are when our derivative is equal to 0, so that's and also when the derivative is undefined. And also we can think about critical points as our relative mins and our relative max values, or potential relative mins and relative max values. So I have a derivative of 0 at the highs and the lows. And then I also have a derivative equal to 0 right at x equals 2. So we have critical numbers at x is equal to -4, 0, 2, and 4. We have intervals of increasing and decreasing. We just look at the graph to see from low point to high point. We are increasing, so from -4 to 1, and then again from 4 to infinity. And then we're decreasing in this arm right here, so -infinity to -4, or from 1 to 2. So, sorry, excuse me, not 1, from 0 to x equals 2, or from 2 to 4. We know that we take a break here at 2, so we don't know if we're decreasing or not right here. All right, we also decrease from x equals 0 to x equals 4. All right, next are relative mins and maxes. So we have a relative max at 0, 1, a relative min at -4, -4, and also a relative min at 4, -3. Our points of inflection are when our graph changes from being concave down to concave up, or concave up to concave down. So I can see that I would draw my tangent line underneath the graph until I get to x equals 1. And then, so this right here is a point of inflection. And I can also see that I would draw my tangent lines above the graph until I get to x equals 1, positive 1. Let's put those right here. And then I would start drawing my tangent lines under the graph. Okay. Then here at x equals 2, again, I'm going to switch to drawing my tangent line above the graph. So that would be at x equals 2. And then my tangent line goes under the graph at x equals 3. And then it stays under the graph, under the curve for the rest of the time. So we have points of inflection at -1, 0, 1, 0, 2, -1, and 3, -2. The points of inflection tell me where I switch concavity. So we start from -infinity to our point of inflection as being concave up, -infinity to -1. And then I move to being concave down from -1 to 1. So from -1 to 1. And then I moved back to concave up between 1 and 2. And then I am concave down between 2 and 3. And then from 3 to 4 and beyond, I am concave up. So I'll go ahead and write that. The purple is concave down. So from -1 to 1, and then again, from 2 to 3. So x equals 2 to 3. And concave up from 0 to 1, or from 3 to infinity. All right, next up is the graph of f prime, or g prime of x. And we have to be really careful here because I get confused and I think that this is f or g regular all the time, but remember this is the derivative of our function. So this represents the slopes of our original function. So if I look at this max here, this would be the output. 2.2 is the slope of the original function. Slope of the original function. All right. So looking back at our chart, we know that the critical numbers of g prime, are the zeros of the g prime graph. So I look at my graph, and any intersection point will basically when g prime of x is equal to 0, or when the graph is undefined, right? Like the first derivative test. So I do, my critical points are going to be when x is equal to -4 and when x is equal to like 2.5-ish. Okay. Now we don't know the y values, so we're just going to say when x equals. We can't solve for the y values right now. We can tell that the graph is increasing when f prime of x is greater than 0, and it's decreasing when f prime of x is less than 0. So I look at my graph and I am going to see that the output is greater than 0 from -infinity to almost -4, and then from -4 to almost 2.5. And then after 2.5, the y values are negative. So we have positive, positive, negative. So if I were to draw that on a number line, 2.5, I would have tested the values to get positive outputs, and negative outputs, telling me this is increasing, increasing, decreasing for the graph of G. So we decrease from 2.5 to infinity, and we increase from -infinity to -4. We take a break, and then we switch from -4 to 2.5. We don't include -4 because that's when the derivative is equal to 0. All right, relative mins and maxes. So how do I find the relative min and max here? Remember, just like a normal derivative, first derivative test, we look at when do we change between increasing to decreasing. So in this case, from positive outputs to negative outputs. We're back. So the relative max, I have no values changing. Oh, sorry, we're changing from increasing to decreasing, or positive outputs to negative outputs. So I'm going to have a relative max at 2.5. I don't know the y value, so I'm just going to leave it. X is equal to 2.5. Our relative min is none. We don't have any intervals where we're decreasing to increasing, so we're good. All right, so how do I find my point of inflection? This is when the zeros of, we're finding the zeros of the slope, or when f of, just kidding. We're finding when the slope is 0. So when g double prime is equals to 0, or in other words, the when g prime's slope is equal to 0 or undefined. Okay, so I'm going to looking to the relative mins and maxes of the graph, because that's when g prime has a horizontal tangent line. I don't have any vertical tangent lines, sharp turns. Looks like I have another relative min here at 5. So we're going to have points of inflection when x is equal to -4, 0, and 5. Okay, at horizontal tangent lines. We are concave up when the graph of g prime is increasing, and when the graph is decreasing, we are concave down. So when g prime is increasing and when g prime is decreasing. So let's go back and look at our graph, and I'm going to do some erasing because this is a mess. All right, so I have my points of inflection here. All right, I am looking for the decreasing parts. So the decreasing parts are from -infinity to -4, and then from 0 to 5. We increase from -4 to 0, and from 5 to infinity. So our intervals are from -4 to 0, or from x equals 5 to infinity. Concave down on the purple parts from -infinity to -4, or from x equals 0 to 5. Last graph is looking at when I have the graph of the second derivative. And we didn't talk about this, so let's go ahead and go back. The second derivative graph only tells us about our concavity and our points of inflection. We really can't infer anything back right now to figure out our relative mins and maxes or anything like that. So there's not that much information we can find out. And a second derivative, remember, it's just like taking the second derivative and applying the second derivative test. If the graph of the second derivative is negative, so when f double prime of x is less than 0, then the function is concave down. And if the graph of f double prime is greater than 0, then the original graph of f is concave up. And then we get inflection points when we switch from being concave up to concave down, or concave down to concave up. All right, So we're looking for positive and negative outputs, and I'll draw my number line underneath because that is what really helps me. Okay. So where do we switch from being positive to negative? Well, we switch from positive to negative when we are at x is equal to 2.5. Okay. And our critical points for our points of inflection are going to be the zeros of f prime of x, double prime of x. Oh, it's h. H double prime of x is equal to 0. So just like we would use the second derivative test. Okay, so another critical point would be at -4. I need to look what's happening with the outputs when our graph is less than -4. Looks like the outputs are positive. Okay. And then between -4 and 2.5, again, the outputs are positive. And then from 2.5 on to infinity, the outputs are negative. So what this tells me about the graph of G is that the graph is concave up, and concave down. So our points of inflection would be when x is equal to 2.5 only. The next part is to figure out, just write our intervals where our graph is concave up or concave down. So we are concave up from negative infinity to -4. Then the 0 doesn't count, so then I move on. And I'm also concave up from -4 to 2.5 without 2.5 included. So, or 2.5 not included, I guess I could say. And then from 2.5 on to infinity. And that is that. These are really tricky. I know.